Yeah, started regarding Rajeev. Go for it.
Okay, so today we will be talking about the topic consistency patterns, and this will be some of the um, things that we will be discussing today may overlap with what we discussed while talking about cap theorem, right? So let's quickly look into what consistency means first, right? So, in layman's term, consistency means uniformity, right? So, if you write something into your database and you read it, you should always get the same value. You should always get the latest value that you have written. So that is what we mean by consistency, right? And we can say that a system is consistent if an update is applied to all relevant nodes at the same logical time, right? So in this is especially with respect to distributed systems where we have replications and multiple nodes having replica copies, and system is considered to be consistent only if all the replicas have the latest written data for any document, right? So let's ask ourselves a question. So say for example, there is a user named Alice and he's writing an object A into a database, and he's doing that at 10 p.m. on a given day, right? And this write operation itself takes around a few milliseconds, right? And say we have another user Bob who is actually trying to read that particular object that was written by Alice into the database, and he is doing that on the same day at 10:01 p.m. after the write is actually completed, right? So will Bob be able to receive that object and read the data in that object, or will he get a 404 resource not found, right? So the answer is it depends. Okay, so we'll look further why I say so. Okay, so before we continue, let's take a look at the brief history of how we have evolved over the years. In older days, or even today, in many applications, we have a database that is deployed on one particular server, one particular node, right? And all the requests are coming to the same database. Say for example, there are users who is firing some requests which is going through a service, and there is a read or write operation done on the database, and the response is sent back to the user, right? This we were able to handle pretty neatly in olden times when the number of requests were relatively low, right? And RDBMS especially did a very good job actually, especially with their ACID properties, in which C actually stands for consistency. So we there was and there were not many occasions in which we had to really think about consistency, because they managed it through maybe locking mechanisms or maintaining versioning during writes and reads simultaneously, and or any other mechanism, for example, right? But eventually, when the number of requests increased, and now we can also consider that number of requests going to the database may be millions per day, right? So we cannot scale this database on a single server anymore. So the only option was to scale out. So in the modern days, we have a database something like this, right? In which we have four instances of the same database, right? In which one is the master, and we have three slave nodes. Consider any request coming in, any write request coming in is actually going through the master node. Okay, and any read requests that are coming in are happening through the slave nodes, right? So any write is going through the master node, and read is happening to this through the slave nodes. That means all the data that is being written into the master node is has to be actually saved into slave nodes as well, right? So this brings, so and also another thing is when we talk about distributed systems, many application support say that they support commodity hardware. So if we are using commodity hardware, then node failure is a norm, right? So distributed systems have to handle and be resilient to node failures, and they have to, so that they can be always available. Hence, we have multiple replicas in the system of the same data, right? So say for example, a user again is writing something into the master table, and right after he's writing it, maybe he's keying in something from his laptop, and right after he has saved something into the database, maybe he picks up his phone and tries to fetch the same data through a mobile application, which is actually happening through one of the slave nodes. So the thing is, will he be able to see it instantaneously? So that's the thing that we are talking about today, and whether he will be able to see it or not, we will find it out eventually. Okay. And this is not only with master slave kind of architecture, but with any of the distributed systems in which we have replications of the data. Right. So, any questions so far? Am I clear?
I'm very thrilled to know whether we will read it or not, Rajiv. Let's see.
Okay. So, without much further ado, we'll take a look at consistency models. So, what are consistency models? Right. So, a consistency model is a set of histories. Basically, what they define is which histories are good and are legal. Basically, that means which of the writes that we have done, multiple writes that we have done, which of them is actually good and which of them are outdated. So this is what consistency models define, or it is a contract between a system and a developer who uses it, basically. There are many types of consistency models, like for example, strict models, eventual consistency, sequential consistency, casual, FIFO, and so on. The list is not limited to what I have written here. There are many other consistency models, but today we will be talking about the first three consistency models only, and later on maybe we can have another session or a follow-up session on this where we can talk more about the other models. Right. So starting with the strict consistency model. Okay. So strict consistency model is the strongest consistency model. It is also sometimes called as strongest consistency model. Right? And it says that a write to a variable by any processor needs to be seen instantaneously by all processors. So any write that is happening into the database, and after that, whoever reads any number of times have should read only the latest value of the document and not the older values of it, actually. Okay. So how do we achieve this? We'll take a look. So consider we have a cluster of the distributed database in which we have three nodes, node 1, node 2, and node 3. And there is a user who is trying to write some data into the cluster. So he writes the data into node 1, and after that the replication takes place. So after the user writes the data into node 1, the same data is actually replicated into node 2 and node 3. And once they are finished replicating, an internal acknowledgement is sent to node 2 and node 1. This is how we make sure that replications are also in sync, right? And the last step is the user gets an acknowledgement saying that the write operation is completed, right? So basically, whenever a write operation is triggered, so it takes some amount of time, right? So whenever it is triggered, so whatever the start time is until all the replication is done and then the acknowledgement is sent back to the user, any other operations that are to be happened on the same data will be on hold, right? So you you may be already thinking that this will induce some latency. Yes, this does, and this there is an impact on performance. So it will have a higher latency, basically. Right? So this is strict consistency model, and what are the pros? So system always returns the latest write value, no matter what. Once write is acknowledged, read always returns the latest value. And even if one or more replicas fail, the system will still have the latest data and can continue to be available. Right? But the disadvantages of this model is a significant impact on performance, especially with high latency processing. So some examples of this model are banking transactions. Say, like, I think we have gone through these examples while discussing cap theorem already, like banking transactions, for example. So anything to do with the latest balance, I think we always have to have the right data on every read. We cannot have outdated data on latest balance of any account. And in case of retail, you cannot sell more items in the than there are in the warehouse stock. Right. So if two users are trying to purchase the same item in which only one stock is available, both of them cannot actually have it. So this kind of model should have a strict consistency. Right. And also while booking flights or theater seats, any booked seat should not be available for other users as well. Right. So this is strict consistency model. Uh, so going forward, let's talk about eventual consistency model. So basically what it says is all replications happen eventually. They become consistent eventually and not at the time of the right operation being done. Right. So let's see how it happens here. So again, we have the same cluster with three nodes, node 1, node 2, and node 3. And there is a user who is trying to write something into the cluster and he writes it successfully. So the next step is that as soon as the user is finished writing the data into one of the nodes, he gets an acknowledgement saying that the write is successful, right? And the user can go back to doing his things. And only after that the replication is triggered. So we can think of this as replication being done asynchronously, whereas in strict consistency models, replication is done in a synchronous mode. So, so these are the advantages and disadvantages. So obviously there will be better performance because user does not have to wait until the replication is completed upon the write operation. And this kind of data is highly available, but it's not highly consistent. Right. So cons here are potential data loss in case of node failure. Say for example, the node in which the data was written into goes down, then no other replicas actually have the latest copy of the data. So again, there will be more inconsistencies in this case. So, and the update happens to all the replicas eventually, and readers get the updated information eventually only. Okay. So there are applications in which eventual consistency models hold good also. Like for example, real-time cricket scores and commentary. So if there are 10 users who are consistently looking at the scores, say for example on ESPN cricinfo.com or something, it's not mandatory that everybody has to get the latest update at the same millisecond, right? They can wait for a few seconds to be updated and there is no harm. but this kind of model cannot be applied in banking transactions, right? So this is all about eventual consistency model. So going back to the question where Alice writes the data into the database at 10 p.m. and Bob's read it at 10:01 p.m. So it actually depends on where Bob is reading from. If the replica is already completed and if the model that is being used is strict consistency model, then yes, Bob will be certain that he gets a copy of the data that was written by Alice. But if the data model that was used was eventual consistency model, then Bob may or may not get the data. He may get a notification saying that the data is not available. Right. So, am I clear till now?
Yeah, pretty clear,
Yeah.
Rajeev.
So, continuing from here, next is the sequential consistency model. So, by the basic definition of this, it is a weaker memory model than strict consistency model. So what it says is, I'll just read out this definition and then we can discuss more about it. So this was framed by Lamport in 1979, in which he says sequential consistency is met if the result of any execution is the same as if the operations of all the processors were executed in same sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. So basically, what he means is, say we have a process in which there are four operations. There is a write, read, and write operations, right? So this model says that each of these operations that are within a single process have to be executed in sequence, right? So this happens in sequence, and say for example there are many other processes, process 2, process 3, or so on. Say for now I have taken only process 1 and process 2. So process 2 also has read, write, and write operations within it, and both process 1 and process 2 are actually trying to access the same memory location. Right. So what this model specifies is every operation within the process should be executed sequentially, but across processes, it can switch between the processes with arbitrary interleaving. Right. So only thing is that this model mainly talks about concurrent access to a memory location. So So when this both the process are being executed, so what happens is either one of the process is started first. Say for example, write operation of process one is started. Once it is completed, only then the next process can start. It can either be read of X in the same process, or it can be the first operation in process two. So it has to happen in sequential order within the same process, but it can switch between the two processes and hence maintaining atomicity at the operation level. Right. So it makes sure that two operations are not being executed at the same time, which are trying to access the same memory location. So let's take an example to understand this better. So in order to talk about one example, let's take a comparison between how this holds good with respect to a strict consistency model. Say for example, this is the strict consistency model. So again, we have Alice and Bob here. So both of them are actually exploring iPhone 11 page. They are trying to access the page and trying to purchase the iPhone 11, which is in which there is only one stock left. There is only one piece left, right? So this is in case of strict consistency. So once Alice So first Alice lands on iPhone 11 page. So this is the timeline. So Alice is the first one to land on the iPhone 11 page, and we can see that he gets a notification saying that hurry, only one piece left. Right. The next thing is Bob lands on the iPhone 11 page now. Even he wants to buy an iPhone and he lands on the same page, but only after Alice has logged into the website. So since the piece has not yet sold, so even Bob sees the same message, hurry, only one piece left, right? So next, Alice selects iPhone and clicks on pay. So here Alice has clicked on pay, and right after the right after Alice has clicked on pay, there is an update fired as block iPhone. So there was one stock only left, and now after this time, the iPhone is blocked, right? So after this, Bob selects the iPhone and clicks on pay because he was on the landing page and he can still see the pay button. So he clicks on pay, and as soon as he clicks on pay, he can see that he can see a notification. Sorry, you were late, or something like that. The phone has already been sold, right? So unsuccessful purchase notification for Bob. And after this, after Alice has done all the payments successfully, he gets a purchase successful message saying that congrats, you got the message. So this is a typical strict consistency model example in which writes are happening and only one write is happening at a time. Yeah. Now we can compare this with sequential consistency model. So in this, we can see again both Alice and Bob are trying to purchase iPhone 11. Both get the same notification saying that hurry, one piece left, both of them. And Alice selects the iPhone and clicks on pay here, right? So update is fired as block iPhone. But if you see, before that operation is actually processed, there is another operation which has switched from Alice process to Bob process, and it says that Bob selects iPhone and clicks on pay, right? So only after that we can see that update is fired as block iPhone, and Alice purchase is unsuccessful here because it was blocked by Bob, and Bob's iPhone purchase is successful and he gets a notification. Okay. So any doubts as of now? Actually, this is the last slide that I have for today.
Rajeev, in the sequential, where does the locking happen, or does lock doesn't happen at all?
Uh, the lock actually, if you see, it is at the process level rather. So, so, so here, if you see, here, so when one write is happening, the so the other processors are actually locked in this case. This is on memory location.
Hello.
Yeah. Hello.
Yeah, can hear you now. Okay. So when a write is happening by a process, the other processes are locked, is it?
Yeah.
So this is sort of saying only one process will be running an operation at any point in time.
Yes. Yeah. That's right. They're happening in sequence, and they do switch between the processors, but at any given point of time, only one operation is being processed. So one of the disadvantages of this, we can say that even we cannot have multi-processing in this case.
Okay.
Rajiv, can you go back to the example, the comparison between the sequential and the strict once more? The last page.
Okay.
Okay, so my understanding in this case is in case of the strict consistency, um, the flow, let's say we are talking about R1, W1, W2, and R4, the whole sequence goes uh, in one go, or I can see if, hello,
Hello.
am I audible?
Yeah.
Yeah,
Yeah,
I
sir.
can hear you.
Okay, my question is still in strict consistency in both the cases, the switching, are there multiple processes taking care of requests from Alice and Bob, or there is a single process that is taking care, or each request in itself is a process?
There are multiple processes in when we talk about distributed systems. So there are multiple processes trying to uh, access the same memory at a time. But in case of strict consistency, when one is writing something into the memory, the others are actually waiting. So it happens one after the other.
Rajeev, the screen share is gone.
Yeah, actually, I took the call on phone, Raja. My laptop switched off somehow.
Okay, no worries.
So somehow I'm trying to because in strict what do you say, strict consistency, still the multiple processes are running in a sequence only, right? I mean, the sequence that you explained in the sequential consistency, if the same sequence occurs in the strict consistency, the I mean, the
Okay.
consistency will be same, right?
Okay. One way to think about it is when we talk about strict consistency, the actual timeline sequence is followed, right? So one user logs in, he clicks on pay and other things. He's actually doing the transactions. As soon as he does something, he clicks on pay button, and then another user comes and clicks on pay button. This actually is happening with respect to time. It is honoring the time, right? But in case of sequential consistency model, it is not with respect to time, but how the processors get the CPU, basically.
But it's sort of time also, right? Because the when you plot it on a line, it is still some sense of time is there. But what I understand is that in strict consistency, the consistency is with respect to the object that is being updated. Because in the strict model, when you reserve a particular phone, the consistency ensures that no other update happens on it, and therefore the other transactions fail. But whereas in the sequential consistency, what is more important is the sequence of operations rather than the lock on the object. So because by the time Alice has paid for it, Bob paid for it. Bob paid. So in that sequence, Bob gets the priority because paid for it. And Alice payment later does not succeed because the sequentially Bob has already won the race. So
Yeah,
so this
correct.
is
Correct.
this is more
So
of
so if
a
you
logical. Yeah.
okay, okay, continue.
Yeah, I just wanted to conclude by saying it's more of a. I mean, we have to go away from processes, number of processes, and all these low-level details, and stick to very high-level logical understanding. In a strict consistency model, the object consistency is the high priority. Therefore, if anyone locks it, depending on when he locks it, he can lock it at the time of reservation, or he can lock it at the time of purchase. If he locked it at the time of reservation, nobody else can reserve and nobody else can pay for it other than this person until he releases it. In a sequential model, we have to understand as if you take all the operations that are happening by multiple people, plot them on the timeline, and in that timeline, If one user has won the race and he wants it, that's it. The rest of them will fail, irrespective of when the lock happens.
Yeah. What you say is right, actually. But also there is another thing to consider is how the processes are executed also. So it is not always with respect to time always in case of sequential consistency. So say for example there are 10 operations listed for process 1 and 10 for process 2. It can happen that maybe process 2 first operation came in, and then after 2 seconds all the rest of the operations came in. But still it can still happen that process 1 to 5 operations has already happened, and then the interleaving happens and the switch between the processes happens. This is also valid in case of sequential consistency.
Well, if we assume that is the case, then there is no way to predict the state of the system at any point in time, because it also depends on when the processor gets its
Yeah,
priority.
yeah. That's why it is not strict. We cannot confirmly say that this is how it behaves. It, it is not the strict consistency model, basically.
Okay.
What are the real life use cases for the sequential consistency?
So basically, it depends on the application. Basically, like for example, one can have the same use case that I was showing, right? Adding it to a cart and then checking it out. Even if one user has added it before another user, maybe the second user gets the priority. Okay. So why we choose this one is because maybe performance and other things when compared to strict consistency model. We don't have to actually follow strict consistency model in this case, right?
Mhm.
Okay, good. Any other questions? Otherwise, I will stop recording for this one. Everybody good? Okay.
Yeah.